Hey gang, let's rap a little bit about a topic that's going to be ever present in our course, that of probability distributions. We've seen data for variables displayed in a few ways now, in a histogram or bar graph, a box plot, and if we think about frequency, it's not too difficult to get to relative frequency or percent, and this is an estimation or an approximation for the true distribution for the population from which the data came from, right? Our data would be what's used into the creation of the histogram, and that's informative. However, we generally want to learn about the population, so that sample info can be used to approximate what's truly happening in the population. And this is also under the assumption that the sample is representative of the population, which is ensured by utilizing the process of random sampling. To do a quick pick here, to jog our memory, if we've got a set of axes, usually we are restricted to the first quadrant in the stats world. Over here we might have percent or relative frequency in some way, and then we've got our variable displayed on the horizontal axis. For now I'll just write the letter Y, but it could be length, height, age, whatever it is. And when we've seen these histograms, I will quickly draw one. What we have seen with relative frequency histograms is that here the heights of the bars should sum to 1. It's often useful to not consider a histogram in its classic sense, but when we think about probability distributions, to consider a smoothed out version of this, so that way there aren't these jagged edges, but more of a smooth curve. And if I was to maybe overlay one of those here, I might draw it something like this. This appears to be skewed to the right. And when we smooth out that curve, we can really no longer consider it as percent or relative frequency, but the way that that would be represented on that vertical axis is as density. We'll touch on that a little bit more. So this is called a density curve, and a distinct difference with these density curves is that relative frequency or probability is not on the vertical axis. Relative frequency, however, is represented by the area under the curve, represented by the area. So for instance, with using a relative frequency histogram, if I was interested in the probability of observing a value, say from 15 to 20, I would simply go to the height of this graph and find that percent, whatever that is. Here, with a density curve or a probability density function, if I want to find that probability, I would need to find the area between these values of interest. I need to find that area. Over here on the left side, we know that all the heights, all the relative frequencies must sum to 1. Fundamental property of probability. Over here, that property is the same. However, since relative frequency is represented by area, here it is the total area that must sum to 1. This area can have 2 interpretations. One interpretation is of the probability of observing these y values in a randomly selected individual, or the proportion of y values in the population between those values of interest. So these are different interpretations, but they are on the same coin, if you will, where this top one is applied to an individual. The chance that an individual has y values, say between 15 and 20. And the second one is applied to the population. What proportion or percentage of the population has y values, say between 15 and 20. Let's cruise into an example. Let's look at the classic IQ score example, in which IQ scores are bell-shaped, also known as normally distributed, with a mean of 100 and standard deviation 10. So I'm going to draw this here distribution. Whee! And I can label my horizontal axis as IQ score. And the number in the center that I'll label would be the mean. Okay. We draw these so often that we often don't even include a label for the vertical axis. Sometimes we just don't do it. And it's kind of a funny practice, but if we were to do it, we would label it density. And it's hard to really say what those tick marks would be at this moment, because remember, the entire area has to be a 1. And you might think about a couple tick marks here, like, 90, 110. I'll just do that for right now. So these y value tick marks, if we were to figure them out, they would be pretty small. I got a question for you to help solidify these 2 probability interpretations. Let's see if we can fill in the blank here. If you recall from the empirical rule, there's a certain percentage of observations that are observed between the mean plus 1 standard deviation and the mean minus 1 standard deviation. Since the mean is 100, standard deviation 10, I'm referring to the region of scores between 90 and 110. So there is a certain percent chance that a randomly selected individual has an IQ between 90 and 110. Maybe you remember this from the empirical rule. That is about 68%. Another way to interpret this 68% would be as the percent or proportion of people who have IQ scores between 90 and 110. So these 2 statements are different, but they are intimately intertwined, right? If 68% of people have this range of potential IQ scores, then it must follow that there's a 68% chance that any individual would have IQs between those values. Let's see how we would get these density values from a relative frequency perspective. Let's look at this graph here with relative frequency, and I would like to draw a histogram here that has some nice numbers for us to work with to facilitate this leap. Okay, I'm going to call these relative frequencies, have heights of 0.1, 0.2, 0.3, and 0.4. So really, we've got relative frequencies of 0.4 and 0.1. Furthermore, I will label our horizontal axis for the variable. Let's call these tick marks, we'll start them at 200, we'll go to 220, 240, 260, 280. What we can notice here is that the relative frequencies add to 1. If I was to sum the relative frequencies, that would sum to 1. Add them up, 0.1 plus 0.4 plus 0.4 plus 0.1. However, what is the area? Well, I actually don't care what the area is, just notice that the area is definitely not a 1. We know how to find areas of rectangles, right? Even this first rectangle would have area of 20 times 0.1. That first rectangle alone would have area 2. So that exceeds 1. Let's retranscribe this information into a new image that will no longer be a relative frequency histogram, but will be a density graph. So we need to calculate the densities that correspond to these relative frequencies. Now, good thing for us, there's only 2 calculations that need to take place, because there's only 2 relative frequencies in this simple example. We've got the relative frequency of 0.1, 0.4, and we need to divide those by the bin width. Each of these classes, from these tick mark to tick mark, that's a bin width of 20. So the density that would correspond to these relative frequencies of this variable would be 0.005 and 0.02. Let's retranscribe our information now as density. So I've copy-pasted our graph. I will label the vertical axis now as density. And the tick marks that I will use will no longer be 0.1, 0.2, 0.3, 0.4, but will be 0.005, 0.01, 0.015, and 0.02. So as you can see, the density values here are quite small in order for the area of this graph within the bars to be a 1. So let's notice now the area does equal a 1. If you were to manually calculate those, length times height, I assure you, you will obtain a 1. Awesome. So one of the main take-home messages from this video is that we are going to be using area as a proxy for probability. And we're going to use these probability distributions in that sort of way. Now you may be asking, how on earth would I find the probability of, say, any location on this graph? Well, we will develop those tools eventually. Hang tight. See you in the next video.